guest speaker, Garth, say something about his interest in geology, and this topic is peculiar because it's one of the branches, in my opinion, between geology and astronomy. I don't know if you're going to go into that part, but you may have happened to read some other things about Garth. He's speaking to us on the Younger Dryas cold event, and he has quite an interesting bio. In addition to what he has told you, you see in front of you that he is from South Wales, UK. My great-great-great-grandfather was from there, I think. And he is interested in mountains and caves and what they tell us. So he samples the waters and the chemistry and where they go. So he was in the RAF. He was an air traffic controller, which is pretty impressive. BS at Millsaps College, MS at University of Southern Mississippi. And he did karst work in Tennessee. And we're just in an unbelievable region of karst, subsurface region and groundwater motions. It's quite interesting. So he's well published and has worked on karst topography in many places. And interestingly enough, he's a fellow of the Geological Society of America. So I'm going to put his PowerPoint up, or you can put it up. But Garth, it's a pleasure to have you with us. So I'm going to turn it over to you and give you this.
Okay, well, it's a pleasure to be here. This is one of those stories where I literally stumbled into things, and I've never worked at a university, although I've done a lot of research. And somebody asked me once why, and I said, and I'll tell you, I just had nothing better to do. And that's the truth. So this view here is of a valley in South Wales, and what you might notice is there aren't any trees in the upland areas. Even so, this was called the Great Forest. So what happened to all the trees? Well, they built a lot of houses in the Bronze Age and Iron Age and the Neolithic in general, and they also had to pen their animals, and the way they did that was by building structures out of wood. And that's really the truth. Okay, so we look quickly at the geology of South Wales and England here, no disrespect to Scotland, but we've got two dots on here, one a yellow dot, which is where a certain cave is that I will refer to, and the other is a red dot, which refers to another archaeological cave where a skeleton was found 300 odd years ago, and the skeleton was covered in red ochre, buried with lots of artifacts, and this became known as the Red Lady of Paviland. I'll go further on that in a subsequent slide. So we have a close-up of South Wales here. Here's the close-up of where the yellow and the red dots mark. The bluish green there are limestone rocks which form karst topography and form lots of caves. So we are in the very south of Wales here, and you notice that the rocks form a rim. In the middle of this is the South Wales coalfield, and those rocks are younger. So we have younger rocks in the middle and older rocks to the north and south. And as you go further northwest of here, you get into progressively older rocks that go back to some of the oldest rocks that we can find on Earth. So here's a labeled version of that first photograph. And if we start off from the bottom here, you can see the rocks down here are 330 billion-year-old limestones, and similar in this part. So the rocks dip in like this angle here. And what you've got here are older rocks, up to 350 million years old. This area was glaciated during the Pleistocene. So we have glacial deposits. This is a moraine, which goes back to the Younger Dryas, which is called the Loch Lomond Stadial in Britain. There were stadials and interstadials, and there were ice advances and ice retreats. The stadials and interstadials were temporary and short period ice advances. The interstadials were short, temporary, warmer periods. This is a glaciated valley. You can see the U shape here, and we do have glacial deposits across the floor. So here, yeah.
Why are the older rocks above the newer rocks?
That's not the case. It just happens to be that way, way I labeled the slide, okay? They are not above the younger rocks. In many cases, like around here, they can be, but this isn't the case here. I apologize for my poor labeling, okay? So here's a depiction of the extent of ice over Wales in the last glaciation. And the star at the bottom there is where our cave sits. So this was underneath the continental ice sheet for a considerable period of time. And the cave was also in the side of a valley that was deepened by glaciation. Okay, so if we go up to the upland area here, which was labeled in the top left of the first picture, then you have this large ridge here, which is called a lateral moraine. So this is the debris pushed to the side of a valley by this glacier moving in the direction that I labeled that here. And this stadial is dated at between 13,000 and 10,000 years old, okay? Now, if you're conversant with the Younger Dryas period, you will realize immediately that that spans the Younger Dryas, okay? So we have a surface deposit here, which is of Younger Dryas age. So if we look at the relief here, this gives you some perspective. These are very steep, very high walls and ridges here. These are the old red sandstone rocks, 350 million years old. So the limestones would be above these, on top of that ridge further down the slope. And we had both continental ice and valley ice here, okay? So we consider that it would be more likely for cave deposits underground to form in the warmer periods as opposed to the colder periods. So I'm doing a long introduction here. Here is a set of figures and some information on the figure in the top left here. Please note the scale. That's age in millions of years before the present. So we're going back 70 million years in this figure here. And what you see is a progressive cooling of ocean bottom water. This is done by stable isotope ratios of oxygen and hydrogen, okay? So deuterium and oxygen-18, actually. So you can see there is a rather continuous cooling from 70 million years ago to today. You notice how steep this falls in this last 2 or 3 million years, okay? So we were heading for another glaciation here, okay? I'm going to say that flat out. There's nobody that can say this doesn't suggest we are heading for another glaciation here, okay? This spike here is called the Paleocene-Eocene temperature maximum. It is now considered to be the result of another impact, okay? By the way, of course, this impact back here is the Chicxulub impact in Mexico, which was a huge 40-kilometer or 50-kilometer body that, of course, resulted in the dinosaurs changing from being large animals on land to just birds, okay? So we've also got a lot of other temperature spikes here, and we've got some valleys, but you can see there's a reasonable amount of noise on this graph. But it shows clearly we've got a decreasing trend in bottom temperature of ocean water. Okay, the bottom graph shows a different scale. This goes all the way back now to the Permian period, and it shows what we have then is another large glaciation at that time, the blue here. And you notice the blue is here and the blue is over here. So this amount of glaciation is not common in 250 million years of geologic history, okay? So here's a different graph that comes from a really wonderful paper by Hay and others, which explores all the reasons for catastrophic events, particularly those involving the word we shouldn't use anymore, climate, okay? What we've got here is a different scale. We've got now from 0 to 5 million years, 5.5 million years ago. And in the top right of this figure, you can see we only had Antarctic glaciation. What happens next is the Panama was open and it closed tectonically. So the ocean plates moved from the Pacific and literally closed the Panama. This prevented circulation from the Pacific into the Atlantic around that part of the globe. You'll see then what it labeled as is the onset of favorable Milankovitch orbits, okay? So Milankovitch was a Slovenian or Serbian scientist that studied the tilt of the Earth's axis and the position of the Earth around the sun in its elliptical orbit, whether the tilt was pointing away from the sun when it was furthest away, or whether the tilt was pointing towards the sun when it was furthest away. And he related this correctly to the sequence of warm and cold periods that we have now documented. However, what you see is that you have this change here from Antarctic only to also glaciation with continental ice of Greenland. Now, before I forget, you can make sea ice out of freezing seawater, but you cannot make continental ice out of seawater because there's no seawater there. What you have to have is precipitation to make snow, which doesn't melt, which makes ice. What you have to have south of Greenland to do that are warm currents, because you can't precipitate from cold air. Okay? So what that did was create this major intensification of glaciation on both poles, near both poles of the Earth. Okay. So somewhere in here it should say, let me see where it is. Okay, Also, there was permanent stratification in temperature now. Okay, and the other thing that happened was the Antarctic Peninsula dislocated from the tip of South America. So now you had a cold current completely circulating around Antarctica. Okay? So you notice here about 1 million years ago, these were what was caused here, and there's a lot of noise in this graph, is there were 40,000 year cycles of warm and cold. And all of a sudden, with the increased ice mass in the north and the south, it changed the tilt and obliquity and all of that in the Earth's movement and changed the cycles to 100,000 year cycles, which we're still in today.
Can I ask a question?
Yeah.
So you were saying earlier that Milankovitch showed that the precession of the Earth was linked to the large temperature cycle of the Earth, the tilt of the Earth during...
And where it is in its orbit.
So, okay, so even though the tilt wobbles every 26,000 years, but so that should match up every 26,000 years, wouldn't that be the cycle? Why is it 40?
Well, there are more than those cycles. I'm grossly simplifying this. Okay, sorry, go on.
Basically, we've been taught in school that the Earth is closer to the sun in our winter and further away in our summer. But that relationship changes over a long period of time. And you combine that with the orbital tilt, and you get ice ages.
Yeah, that's exactly correct. And what happens is that the mass of ice on the Earth being added in Greenland also to Antarctica. By the way, before this, Antarctica didn't have any ice either. Okay? So this is very complicated. But in this period of 5.5 million years here, there's all sorts of other stuff buried in these data, by the way. 5.5 million years ago, we had the lowest sea level. It was incredible. The Mediterranean was dry. The Black Sea was dry, okay? That's why, by the way, you have the deepest cave in the world now on the southern or the northern coast of the Black Sea, okay? I'm not quite sure how to get into why sea level dropped so precipitously 5.5 million years ago. It did, okay? Now, what's more interesting about that is, wouldn't it be great if you had been sitting in Gibraltar when sea level rose back up and you had this tremendous waterfall from the Atlantic refilling the Mediterranean? Okay? By the way, sorry, go on.
Have they correlated how much more ice on the planet changed the orbital velocity?
Well, it's not in hundreds of meters, it's many kilometers. So it
Speculated in a popular science article in 1986, that's what you got.
Right.
It's kind of like a skater putting arms on and spinning faster.
Yeah. So it's very complicated. So in the bottom of this are from benthic foraminifera, benthic micro animals, and the Vostok ice core, which is from Antarctica. These are the temperature and isotope curves, and as you can see, they match. All the other curves just add to what they are is axial tilt, eccentricity, longitude of perihelion, precession index, and obliquity. I told you this is very complicated. When you put all these curves together, what was happening makes sense, and that's how you can reconstruct. Okay, so very quickly, here's one. On one scale here, you've got the ice coring data, European project for ice coring in Antarctica, and it basically looks at climate and the extent of sea ice, okay? So, so let's drop to Pavelin Cave on the Gower Peninsula. This is a cave that is, you can see it's right on the coast here. Now, there's another view of it over here. Remember what happened at the end of the last glacial maximum was that sea level rose about 130 meters, okay? I've been working in Florida. Florida Coast is flooded. It was not flooded before that. So if you go to Wakulla Spring was a giant hole in the ground with a vertical drop into it. That's how all the megafauna got in there. If you go to Wakulla Spring, you can see the mastodon bones on the floor of the spring. It wasn't flooded back at that time. But Pavelin Cave had this burial, and this information was gathered, and of course, the first thought was this is a Roman prostitute, okay? Sorry, they were misogynistic then, as they are now. So this had to be a woman, and of course the Romans did it, okay? The Romans occupied Britain from 56 BC to about 400 AD, okay? Well, of course, it turned out to be a man, and it turned out to be nearly 30,000 years old, okay? Which was quite fascinating because some of the artifacts he was buried with didn't come from Britain. They came from further and further across Europe, okay? So there was a vast amount of trade going on, and interaction and migration throughout that part of the world. Okay, so let's look at late Paleolithic Britain. This is right where I was born and brought up. We used to do fantastic ice climbing on those cliffs when it got cold enough and it froze. These are standing stones. Some of them are called avenues, and they are, this one in the top right, this is a burial kist. So this was covered with an earth mound. The earth's already all gone. And this was a burial chamber underneath here. This is called Arthur's Stone on the Gower Peninsula. Some of these, you notice, are lined up. Some of them actually line up over a hillside. So you can go several kilometers away here and find a corresponding stone that is set up in a vertical position. Most of these are probably glacial rocks that were transported here by ice. So some of them are not the bedrock that they're sitting on. But anyway, so here, of course, are Neolithic henges. And the one in the bottom right should be familiar to you, that's Stonehenge. But the one in the top left is way more interesting. First of all, it's 3 times the size. And there is a fantastic pub in the middle of this henge that serves phenomenal beer and really good lunches. Now that's Avebury, which is not so well known as Stonehenge, but there it is anyway. So these ain't, sorry. Burial mounds. There are burial mounds near there in another place west of Stonehenge called Kennet. Kennet Barrow is a famous one. There is also a huge hill that was built of just earth called Silbury Hill, okay? We went on a field trip here with the British Geological Survey. It was raining all day, and the geologists on the field trip, of course, migrated to the pub very quickly on this field trip. So this occurred during the warming period after the last glacial maximum. The Earth was warming up nicely, and suddenly in what is considered to be 100 years or so, there was a rapid cooling that lasted 1,300 years, okay? The date of it is fairly well established at 12.9 thousand years before the present. There are many sites and many dates. It is not in question. The Clovis civilization died out because of this climate change. It was preceded by a warming period, or a warm period called the Bowling-Alerud interstadial, and the best explanation for that was a disruption of the AMOC. The AMOC is the Atlantic Meridional Overturning Circulation, which is a stratification of fresh and saline water in the North Atlantic, south of Greenland and Iceland, okay? The Younger Dryas, I told you, is Loch Lomond Stadial in Britain, and the Younger Dryas comes from this yellow wildflower of the rose family, typical of these Arctic environments. Very recently, well, there was a cosmic impact explanation for the Younger Dryas. And this became a very difficult thing for the archaeologists to accept, and to a large extent it still is. However, here's a graph showing the sort of temperature difference in the Younger Dryas and ice accumulation, and in meters per year, okay? So it was abrupt, very abrupt, and it lasted quite a long time. We don't live in any scale big enough to understand what 1,300 years of extreme cold would be like. We'll bump into this later. Trust me. Okay, this is about the same stuff, but I'm going to tell you here that the Younger Dryas impact, the main paper, the seminal paper, is Firestone and others, 2007. It is a NASA group, Comet Research Group, that wrote a paper which finally said the Younger Dryas was caused by a cosmic impact, okay? So what was it? It could have been many things, of course. We all understand that. The Centaur objects, Trojan asteroids, something from the Kuiper Belt. And remember, of course, a few years ago, Oumuamua flew past us, which was pretty amazing. And the trajectory of Oumuamua and the path of its entry into the solar system shows us clearly it didn't come from the Oort cloud or the Kuiper Belt or anywhere near the solar system. It came from somewhere else. Anyway, so actually our plate tectonics on the Earth may have began because of massive asteroid impacts and the burial of a very large object somewhere in the Earth's mantle that creates today a huge amount of disruption of normal heat flow from the core out to the crust. The other one is that Martin Sweatman from the University of Edinburgh had a grad student who got interested in a site in Turkey, which I'll mention, and they ended up coming up with the idea that the impact for the Younger Dryas may have been the breakup of Comet Encke and related to the Taurid meteor shower, okay? By the way, Tunguska in Russia happened about the same time during the Taurids, okay? Remember, we know comets break up. Remember Shoemaker-Levy? We saw it break up. All comets have a tendency to break up. Okay, where's the Younger Dryas crater? Well, we've got an interesting crater in Mexico with Chicxulub. It's 180 kilometers in diameter. Still difficult to find. Now, if the Younger Dryas happened at 12,900 years before the present, we know that, it was likely that it could hit the still largely intact Laurentide ice sheet in North America and Canada and the Arctic. So there is now a candidate crater in south of Maine in the Atlantic called Montargis. But the whole thing about the Younger Dryas is, as you will see, well, we'll see in a minute, the ejecta blanket for the Younger Dryas event is absolutely enormous. It is at least hemispherical, if not global. Okay? So this was not a small event. I went here a few years ago traveling with my daughter. She's a traveling surgical tech. Who's been to the Barringer meteor crater? Okay? The rest of you, please go there. Okay? It's worth it. And this was, look, this was a 50-meter object. The crater's 1.2 kilometers in diameter. But the point here is Barringer had so much pushback on this being an impact. He spent about 10 years in the end, and the reason they said, oh, it's not an impact, they said, where's the meteor? Where's the meteorite? Okay, so anyway, so quick slide. It could have been in oceans. That would be difficult too. But we now have really good ocean floor mapping because airlines like Air France and Malaysian tend to land in oceans without much planning compared to landing at airports. Sorry, I shouldn't have said that. But we have to find these bits, and we therefore have these very nice maps of the floors of oceans. So I'm going to go to the last but one bullet here. I found a set of papers at the Geological Society of America meeting, which had a paper which looked at the periodicity of 100-kilometer impact basins and what their periodicity was. And the theory is that this is caused by the solar system wobbling up through an arm of the Milky Way, and that disrupting comets, Kuiper belt objects, and other things. And guess what the periodicity is? It's 65 million years, okay? So when was the last big one? 65 million years ago. Shall we run outside and look at the sky? We're due for one, okay? If that's correct. Anyway, so here's a map of 200 odd craters that are still, you know, observable, or there are 200. And these are, you know, 5 to 90 kilometer structures with a periodicity, as I said, of 60 million years. Okay, airburst events. What these do is they explode above the Earth. They don't actually hit the ground. Fragments do. 2 of these happened in Russia. One was Tunguska in 1908. The other one was Chelyabinsk in 2013, okay? So compared to Mount St. Helens, 596 square kilometers. Tunguska, 2,100 square kilometers. Chelyabinsk, 7,200 buildings damaged. Go to YouTube and find this video and listen to the bangs. It's quite incredible, okay? So you can have these massive events that affect the Earth's surface, and there's no object really to find, although you can find bits and so forth. Okay, so let's go to the Younger Dryas itself, the boundary. This is a site, Murray Springs in Arizona, and this is a Clovis site. What you have here in the middle of the picture is this black mat. This is an organic layer of burnt organic material. You can date the base of it at 12.9 thousand years before the present. That is the Younger Dryas boundary. Okay, the other characteristics of a Younger Dryas boundary are a black mat, magnetic microspherules. Somebody has based on the counting of all the sites now that there could be 10 million tons of magnetic microspherules from the Younger Dryas impact. The third is nanodiamonds of a particular crystal structure called lonsdaleite, which you need very high temperature and pressure to form. Shocked quartz, a big platinum anomaly, and other metals. Fullerenes, specific types of carbon crystals, and the age. So when you put all these together, these make up the criteria for a Younger Dryas site, boundary site. So an ancient civilization in southern Turkey at a site called Göbekli Tepe have recorded in the sky 10,900 years before the Christian era, or about 12,900 years before the present. And the likelihood is, as far as Martin Sweatman, in a superb set of videos on YouTube called Prehistory Decoded, that this was a memorial to watching the results of the breakup of Comet Enki, okay? So Sweatman had a student from Greece who told him about Göbekli Tepe, and he did a master's degree, and they wrote some papers together, okay? So this ends up being Tauric meteor stream, and there is a huge amount of evidence now that points to the Younger Dryas being a cosmic impact origin. Here's a map of the debris field early on in the investigation, and the furthest one to the east there, 22, is Göbekli Tepe. And you can see there are many in North America, and one in Mexico, and several in Britain, one in Greenland. Okay, so here's Göbekli Tepe. There are many of these very large standing monolith stones, almost like 2001: A Space Odyssey, that have inscriptions on them. So Sweatman and Tsikritsis, they looked at these inscriptions and they did something rather interesting. What they ended up doing was realizing that, and it wasn't just at Göbekli Tepe, but these inscriptions tend to turn up at other archaeological sites across that area. And some of them are quite easy to relate to scorpions, winged birds, and the top layer there, or the top set up here, sad to say that they simply refer to these as handbags. Okay? Please don't laugh too hard. But they really are called handbags. But what's interesting is that if you go to Stellarium, I don't know if you use Stellarium, but on Stellarium you can actually put yourself at Göbekli Tepe, And you can dial a date back to 12,900 years before the present and see what the sky looked like. And they did a statistical fit of constellations with the inscriptions on Pillar 43 at Göbekli Tepe, okay? And they, in other words, Lord Raleigh said that if you're doing science and you can't express it in numbers, you're not actually doing science. These guys actually did that, okay? And by the way, that's one of my things I've always believed in. So you can see here, this is out of one of their superb videos on this YouTube channel, Prehistory Decoded. And so they match these with constellations. Okay, so let's review this. We've got very strong evidence of an impact. Nanodiamonds, magnetic microspherules, the black mat, a platinum anomaly, a huge ejector that contains these features, blanket that exchange these features, correlated stratigraphy across North America. And it relates to, as far as the Comet Research Group and many others, it's the breakup of Comet Encke and the Taurid meteor stream, okay? Led to the disappearance of megafauna, the Clovis culture, and few criteria, few concepts fit this list quite as well as an impact. Okay, so now look at a later map of confirmed Younger Dryas sites. Now we've got this site in South America, and we've got a site in South Africa, right? So this was a global event. This was nothing small. Okay, that's the introduction. Any questions? Yeah.
I understand the isotope signatures of temperature, but you plotted temperature against isotope. What other evidence do we have besides the isotopic signatures, and ice core, and foraminifera?
For the cooling?
Forget the temperature correlation.
Yeah. Not much. Yeah. Yeah, what other than the isotopic evidence do you have for the cooling? Okay? And it's, you know, if you believe how stable isotopes work, you can't get out of it that they were cold and warm periods, okay? Because if you look at the rest of the data, you end up with sea levels, right? So your sea levels drop. You can look at evidence from shorelines that show evidence there was sea ice and then no sea ice, and they sort of correlate, right? But that's a really good question. And you have to be skeptical, because we're resting a lot of stuff on this.
It's a minor point compared to the rest.
Yeah. So let me say one thing. Martin Sweatman at the beginning of his video says, before we go through these 21 videos, which by the way, if you want to see how to review technical papers, please watch Martin Sweatman's videos, okay? I'm going to tell you now, you will never want to send a paper to Martin Sweatman to have it reviewed, okay? You will not, okay? He is, if I was teaching, I would say, want to know how to do science, how to review a paper? Go and look at these 21 videos. You'll see nothing better, okay? And I mean that. Prehistory decoded. Okay, let's go back to South Wales. So, a long time ago, an old friend, Keith Ball, worked for the British Geological Survey, and I contacted Keith in the early days of good email, and I said I had just done a master's degree dating cave deposits, why didn't we go to these caves in South Wales and collect some? Because we had Derek Ford at McMaster University who could date them for us. And Keith said, great idea. So I went over to Wales. My mother was still alive. I'd go over and visit her, and Keith and I would go underground and collect samples, okay? We were familiar with these caves. So we were interested in how old this cave was, because it was in a glaciated area, and most of the conventional wisdom was that these caves were all related to the Pleistocene, okay? So from 0 to about 2.5 million years ago, okay? And that's what we did. We collected samples, and we wanted actually to do a little bit more than that. We went underground and found, in one case, a piece of travertine, calcium carbonate, that was precipitated. The remnant of it was on a wall, and on top of it was a sand, and on the bottom of it was stuck a gravel. So this was a passage that formed that had a false floor here that was cut down by water, and we could get a date for that by dating that deposit in the wall, okay? About 73,000 years ago that happened, okay? We got other dates, and they didn't agree, so we had to look at them generally, because we didn't realize how complicated doing geology the way we thought would be, because it just is that way. But that's what we thought we should do. So my mentor from a long time ago in the 70s, Noel Christopher, did this as well. And we never realized Noel and people were doing it, and they didn't realize we were doing it. But we had, in other words, two sets of independent measurements that we could compare. They actually compared quite well. So we didn't date any clastic sediments. What are clastic sediments? These are sands and muds and siltstones that are not made of calcium carbonate. They're made of silica, okay? We didn't do those, but we can do those now. We did think about doing paleomagnetism on them. What is paleomagnetism? The Earth's magnetic pole has not stayed in one place. And the lines of force, as you will know, tilt. They're generally flat at the equator, and they get to nearly vertical near the pole. So you can take that tilt, and you can take the direction of that magnetism that is preserved in the sediment, and basically try and make some sense out of it. Now, what was interesting was that 780,000 years ago, there was a complete magnetic reversal, where the South Pole became the North and the North Pole became the South. We wanted to know whether these sediments were reversed, which meant they were possibly older than 780,000 years. By the way, it gets complicated because 1.2 million years ago, there was another reversal. And then you go through a lot of other reversals, okay? So we may have gotten into a complete mess here doing this, but we are saved by the fact that the paleomagnetism guy at McMaster University had gone on sabbatical for a year. So we couldn't get them done, all right? So that all fell behind. And now you can do them by beryllium-10 and aluminium-26 isotopes. These begin as oxygen-16 and silica-32. They are hit by cosmic particles. Those spallate neutrons off them. They create these two isotopes. When they are buried underground and no longer in sunlight, the radioactive decay clock starts. And you can date up to about 5.5 million years before the present, we didn't do that. That would be nice. So how do you do uranium series dating? Well, so U-238 decays by alpha to thorium-234, which decays by beta to protactinium-234, which decays by alpha to uranium-234. U-238, we all know, has a 4.6 billion year half-life. That thorium and protactinium in between have half-lives of days or hours, okay? So by the time they have formed, they're already making U-234. The U-234 decays by alpha to thorium-230, okay? 4 mass numbers, all right? So what's cool is that a stalagmite or a piece of travertine, uranium is soluble. So you can incorporate uranium in there and no thorium, because in those same geochemical conditions, the thorium is insoluble. So you can trap this uranium in this deposit and the clock starts. You can date it. Now the half-life of thorium-230 is about 75,000 years, so it's about 5 of those. So the maximum would be, 5 sevens, 350,000 years, right? So we may be able to get to a deposit that's 350,000 years ago old, or one that's just got enough uranium in that's really young, but we can date in that range. So one problem is mud. Mud contains detrital thorium. It's thorium-232, which is a primordial nuclide with billions of year half-life, and the other is the thorium-230 that came from the uranium decaying anyway in the cave. So if you incorporate that mud in the speleotherm, there is thorium in there, thorium-230, that did not decay from the uranium. So the age might be wrong. We can evaluate that by looking at the ratio of the 2 thorium isotopes, and we may be able to do an isotron type plot and correct that age. But more recently, we've had another advantage of being able to use a thermal ionization mass spectrometer, where when I did this, I did all of this, all the chemistry, all the counting and everything. You got to drill about a 1-inch core out of the damn thing to get enough uranium in there to do the chemistry. And do the counting. Now you can use a dentist drill to get tiny amounts from a single growth layer and run it on a TIMS machine, okay? So here are the 2 caves. This is the cave in red where Noel was working with his group. This is the cave here where Keith and I were working. So we've got 70 kilometers of cave passage here, horizontal, and we've got a total vertical extent of about 310 meters. This is the deepest cave in the United Kingdom. Our cave deposit came from somewhere around here. Okay. So caves have lots of mud and clastic sediments in them. As I said, you can date these now by optically stimulated luminescence, maybe, or beryllium-10, aluminium-26. Okay, so this is either very simple stratigraphy like we see on the surface, where the youngest rocks are on top, the oldest on the bottom, and we also have other things like in Paviland Cave, you have human remains, you can date some of those bones, and you have paintings on the wall. This is in the Lascaux Cave in France, and you can see that dates back to nearly 30,000 years here. But so we can do some work on these, and then you get something like this, I'm going to give you a test after this on how your Welsh pronunciation will be, okay? This is Ogof Gwynt Aira, and it means cold snow cave, okay? But look at the varved sediments here, and these are probably glacial sediments, okay? This shows us these were all deposited in fairly still water because they're nice and layered. But they could be much older than the Pleistocene. Pleistocene, 2.5 million. There are sediments dated in Big Bone Cave on the Cumberland Plateau here that are up to 5.5 million years old, okay? And that's late Miocene, okay? There are older ones than that. But this technique only goes to about 5.5 million. Okay, so here's a log probability plot of our data plus Noel's data. And you can see we've got a distribution here which has a bit of a gap in this part of the graph, which would be roughly corresponding to the end of the last glacial maximum, and the Younger Dryas sort of falls in here too. These are interstadials, these are warm periods that have been documented using other data from the surface. In the cave here, we do have these two distinct colored sediments. We have a maroon sediment for these older samples, older samples, and we have a browner, sandy sediment from the others. We never advanced on that research. We ran out of time, patience, and money. Here's another depiction of, this time we're looking at deposits from across the UK. So we got lots of data. Anyway, so a small stalagmite that was lying on the floor. Keith and I walking down this passage here. It's got a sandy floor. We walk past this deposit. It's a little stalagmite about this high, but this big. And there's a tape around there so people don't walk into it, but somebody had kicked it over. So I said, Keith, what about this? And he said, looks pretty pathetic, throw it in the bag. So we picked it up and threw it in the bag and took it out, and so nobody would kick it over anymore. Boy, what a good idea that was. But we didn't realize it at the time. Now, we had dates from this set of passages that said we had a minimum oldest age of about 160,000 years for certain bits of this. So, okay. So here are the Younger Dryas. So here are the stalagmite data done on a thermal ionization mass spectrometer. And so we have the base of the deposit here. And then we have another layer. Then we have a muddy layer with no calcite. And we have another layer and another layer. And these are the ages. So the first thing that's nice here, the ages are all in sequence. So the youngest is at the top and the oldest is at the bottom, okay? That doesn't always happen. My master's thesis has some horrible problems like this that it's not possible to explain. I did it by alpha counting. This is a stalagmite this high, and we did it on a TIMS machine, same problem. We submitted it for publication, and they said, it's no good, your dates are all wrong at the top. We can't explain that, okay? So what's cool about this one is, and I didn't mean to pun there, look, we have a range here that is generally before or during the early Younger Dryas, and we have a range up here which is clearly after the Younger Dryas. So this muddy layer, where there was no growth, we say represents the cold period of the Younger Dryas, where this thing stopped growing. Okay? These dates with asterisks are corrected thorium-232 ages. So we consider there's enough detrital thorium-230 in there to question the age. And you can notice that these two had ratios less than 20. That's the criterion we use. So these ages are corrected. This is good. It has a huge, nice thorium ratio. This has a big thorium ratio. So we sort of trust those. Okay, so any comments on this table? Throw all your grenades my way, please.
No growth because it was all tied up in ice.
It was cold. It was cold, okay? We know it was cold because there was a valley glacier with the early slide of this, remember this lateral moraine. So we got the same age there, and that's only 1.5 kilometers across the valley, by the way.
I know what moraine terrain is, but if other people in the audience...
All right, so moraine is ground up rocks from glacial action, okay? Remember, we had two things going on here. We had a continental ice sheet that covered the area. We also had valley glaciers. Now, this cave was actually split by a glacier moving down the valley. We actually found the top entrance of this cave that was literally only filled with a bit of moraine material. I haven't mentioned that. There was a horse skull in there and some deer bones, okay? We sent these to the National Museum of Wales in Cardiff, and they disappeared forever. They never told them that's what they did with them, and I asked them in several emails, and I never got a reply.
It's simple. They're arrogant. They would not accept the figures.
Well, I don't know.
Their perception.
Yeah, I don't know, but it was rather problematic because the horse could be, I think they actually said it was modern horse, okay? The deer. So the question you lead yourself into here is, how did these megafauna survive the Younger Dryas, right? If the others died out, the mastodons, the rhinoceroses, and all the other animals all died out, how did this horse and these deer survive? Well,
They're normally afraid of dark, cold places. Somebody had to lead it in there.
well, it was just shoved in there by the moraine from the side of the valley. But what the explanation is that a lot of these animals ended up in forests, quite deep, thick forests. And they could have survived just enough to live through some of these periods, even though that was many generations and 1,300 years, okay? So that's a whole other thing. So let's go to, sorry, go on.
What analytical technique do you use to differentiate the isotopes?
Okay, so uranium-234 is soluble in the cave deposit. So it gets trapped in it as it precipitates.
Yeah, that's chemical separation, but do you use a mass spec or what?
This was done on a mass spec.
Okay.
This was done on a TIMS machine. And the reason it was good to do it was the errors are much smaller on the TIMS because we can drill out individual layers with a dentist drill. This thorium we're dating with has a 75,000 year half-life. So it's not that hot. And it decays by alpha, by the way, to radium-226, okay? You know, thorium is insoluble in this water when uranium is soluble, okay?
Natural chemical separation.
Yeah, you've got a +6 ionic charge with the uranium, you've got +4 with thorium. They're not going to live well with each other in the same water. The thorium's going to precipitate out. And this whole process of having soluble and insoluble isotopes in the decay chain is called disequilibrium. Because, you know, ideally, you start off at the top of the chain and you decay, and you get to the point where all the short-lived isotopes catch up with the parent, and the activity ratio can become 1, okay? Well, it doesn't happen when these insoluble things drop out. It gets worse below thorium. You go to radium-226, which is because the thorium's in the sediment, it's in the sediment. Guess what's next? Radon-222. It's an inert gas, right? And extremely soluble. So it gets in the water. It decays to polonium-218, and you get into this mess of polonium and bismuth and lead isotopes that are all beta decaying in microseconds. And in the end, you get down to lead-206, but that's way below this. Polonium is extremely toxic because Vladimir Putin figured out how to kill Alexander Litvinenko in a cafe in London with 1 drop in his cup of tea, okay? So you can't fool me and a lot of other people when you deal with uranium and decay series, because if we see a decay isotope, we know what was there. If we see it separated from everything else, you know, of course, we all know. That's why the waste here became classified, right? People like me, if I'd have seen the waste, I knew what was going on here, okay? And the waste, by the way, was many large volumes more than the product. Of course, you know that. Okay, so let's now speculate on the Younger Dryas impact. So here's the Laurentide ice sheet. And we've got the date. So if it hit somewhere in the Laurentide ice sheet, where did it hit? Well, we have these extremely strange bays that form in North and South Carolina and some in Virginia and others in Nebraska. They are really nice elliptical bays. They're called Carolina bays. So if you project backwards from the long axis of these ellipses, they all cross here somewhere in the Great Lakes and suggest that this was an impact somewhere in the Great Lakes that sprayed this material. Here's a LiDAR image of the Carolina bays. Here's a close-up of them. Here's an even better close-up. So Antonio Zamora is spending his entire life and energy on being sure that people realize that these were caused by impacts. Were they caused by impacts of metallic meteorites? And no. He considers these were caused by comet fragments, but not the impacts. The impacts were caused by ice blasted out of the Laurentide ice sheet. Okay? And he has done a phenomenal amount of work on this. He's got this, let me see. Here's, if you look at the bottom 2 experimental results here. Let's go back a couple of slides, so, well, let's go to this next one. So what he's saying is these are funnel shapes that are sliced off by a horizontal surface, and that becomes an ellipse, okay? So not too long ago, a pond in a Carolina bay was cored, and the data for that core were published. Sorry, I don't have a reference here, but guess what? You've got a platinum anomaly. You've got a cuneiform carbon, which is seen at other Younger Dryas sites. And you've got a lot of other stuff here that points to the same type of horizon as a Younger Dryas horizon. I am aware now more of these Carolina bays have been drilled, and there are more data that support the impact. But it's still, this is, if you think the Younger Dryas impact was a pushback. This Carolina Bay thing is, I mean, it's absolute intercontinental ballistic missiles going to people. How dare they say these are impacts? I've got a friend who works for the US Geological Survey. He's convinced they're thermokarst, okay? They're not thermokarst. But anyway, so we'll just, and again, the diagnostic criteria is the date. So if you find a horizon you can date here, and it's 12,800, 12,900 years before the present, that's what it is. So Antonio Zamora put together a timeline here, and he's got ice boulders re-entering the Earth's atmosphere at Mach 11, and he's got ice being sprayed into the very high atmosphere, okay? So, so let's summarize. Stalagmite from this cave in South Wales. The interesting thing for me, does that muddy layer have a platinum spike? Does it have Lonsdaleite? Hard to say it could get there, because remember, we've got to get the water from the surface to enter the cave and make the deposit, okay? So, as is typical, the original sample is missing. Because Derek Ford retired, they changed the department to both geography and geology. No disrespect to geographers, but, and all the samples, which I saw with my own eyes and touched them with my own hands, were moved out of the basement to a storage facility. We hope they're there. But if somebody could find more deposits like this, by the way, the one we have may be unique. I can't find anybody that's dated anything quite like that, a single deposit that spans the Younger Dryas. So, there's a consequence of this. How did the Younger Dryas last 1,300 years? Well, it's this AMOC, maybe. This Atlantic meridional overturning circulation. How do you get there? So you impact in the Laurentide ice sheet. You form Lake Agassiz in southern Canada. Lake Agassiz overflows because you've now caused massive melting. You flood the Arctic Ocean from the Mackenzie River with fresh water. You flood the Mississippi and the Gulf of Mexico with fresh water, and you flood the Atlantic via the St. Lawrence River. So you overwhelm these saline water bodies with fresh water. And you might just disrupt the AMOC, and it took 1,300 years to reestablish. Okay, now, it's up to you whether you want to believe that, but let me tell you, there are 2 or 3 papers out there today that say our monitoring of the AMOC is way behind schedule. It may be 5 decades out of date. And one paper suggests that the AMOC might flip with about a 40% probability in 2037. The AMOC flips, we will have a permanent winter in the Northern Hemisphere. Here's the dates are, or the temperatures are, if you go to a bay in northern Canada and look at the temperature, it's -30, -40. If you go to the same latitude in Bergen in Norway, it's 4 degrees C, right? That's the influence of having the AMOC produce all this warm water going to the shores of Britain and having palm trees able to grow on the coast in southern Britain, in Cornwall, and all of that warm stuff over there. If you cut that off, then Norway becomes this -30 winter. You don't need to melt the ice cap. All you need to do is change the amount of fresh water in the ocean. So you put such a volume on top of the saline water, it starts to, remember this stuff actually has this conveyor belt around the Earth, okay? That is the AMOC. And if you change that AMOC, you have, by the way, you will have vastly more tropical storms in the intertropical convergence zone, okay? We're already seeing that. These two papers admit, and by the way, the climate scientists, they've not ignored the ocean temperatures, but they haven't paid enough attention to them. And they haven't related the ocean temperatures to the air. Okay, so we may have some very interesting futures if some of us live long enough to see it. Okay? 2037 in a long time. It's 12 years. Okay? All right, so here's one for Art. Art's a pilot here, retired pilot. This is an actual picture, so I'll end there, but thank you for listening, and I'll entertain any questions. Yeah, I'm sorry.
That picture of Hudson Bay that you had up there.
Yeah.
There's this semicircle on the east side.
Oh, yeah.
Did anybody do any core samples in there to see if that's an impact area?
What we're talking about is
Right there, stop right there.
is this thing.
Scored sheet, that little half
Yeah.
circle right there.
Yeah.
I swear to God, it looks like a
Look, I don't know how anybody doesn't think that's a huge impact basin. There is a massive one over here called Manicougan. Okay, Manicougan's a big one. But there is stuff now looked at on the floor of the Great Lakes that shows what they claim to be an impact basin. Okay?
I've seen some pictures of some of the provinces that I used to travel out there when I was a truck driver.
Yeah.
And I think it was might have been in Astronomy magazine. It looked like a series of impacts, like something came down and broke up.
Right, right. Yeah, yeah, I agree completely. I don't know how you don't call that a massive. Now, remember, we've got Sudbury Basin in Ontario down here. That's 1.2 billion years old. Maybe not quite as old as that, but it's an old one.
Speaking of magnetic rocks, they found a crater in Germany, south polar magnetism on the rocks.
Mm-hmm.
One time it flipped.
Yeah. So the other one is, there's a crater being found in this part of Greenland here, which is called Hiawatha Crater, okay? That was thought to be the Younger Dryas impact crater. It's too old, okay? It's too old. And some of the early data suggested it was a little younger, but it's actually too old.
How thick was the Laurentide ice sheet?
Here's the extent of it here, look.
Yes, but how deep? I mean, how thick?
Oh, if it was an ice sheet, you're talking about many kilometers.
So an impact would not necessarily leave any evidence behind. You want that? If it took out a chunk of that ice, the rest would melt it.
Yeah, that's correct. And the other thing is, remember, that it was already melting. Remember, this was considerably after 20,000 years ago. So it had done a lot of melting and formed Lake Agassiz. Okay?
Yeah, I had heard
Sorry.
Chicago is under 3,000 feet
Yeah.
of ice.
Noah had a question.
I was just hoping to see the slide of that timeline. You went past it pretty quickly.
Yeah.
Peruse it for a minute while you're answering other questions.
So, yeah, I flip past this quickly because I don't disagree with it, but I've never been able to do the research to come up with how Antonio Zamora came up with this timeline. So the reason I wanted this slide in was just these two pictures down here. By the way, when I was a youngster in Wales, I got extremely interested in Apollo. And I listened to a USGS geologist called Gene Shoemaker talk about impact craters. And I actually made a box, and I put in it several layers. and I threw ball bearings into that to see if I could get the bottom layer to be on the edge of the impact crater. And guess what? I came over here and I never did planetary geology.
The odd thing about that crater in Arizona, you
Yeah.
can see where the rock strata is.
Oh, yeah.
The impact.
Yeah. So I'm about to maybe change my affiliation at GSA from the karst hydrology group to the planetary group. Because I've got some friends saying, oh, come over and enjoy yourself with us.
A little more open-minded?
Well, what you all know, what we end up doing in graduate school is somebody says, I've got a piece of equipment, would you like to use it to do this with it? And you say, oh, heck yeah. And it was date cave deposits. So that's what I did, you know. So it's the occasion that you stumble into. Sorry. I think I'm out of time here.
You have a cup? You have a cup? You have a cup? Garth, we'd like to present you with a cup in appreciation of what you've done for us, enlightening us.
Yeah?
And, but our treasurer has a cup, and we treasure these. There are no more being made.
Yeah.
So you have one of the last ones.
Excellent talk.
Thank
Thank
you,
you. That
Shake your
is
hand.
so cool. Thank
Look
you.
at the camera.
Yeah. Thank you ever so much.
Okay.
All right.